So we were talking about that extra term in that derivation there, and that extra term is exactly something called the covariance. So the covariance is a summary measure of two variables simultaneously. So up until now, we've only been talking about a summary measure of a single variable. So expectation is the population average of a variable. Variance is how far away from its mean a particular variable is. Covariance tells you a relationship between two variables. And the question it's trying to answer is exactly this. It's on average, is x far from its mean when y is far from its mean? Because you could imagine that there's certain variables where, like let's say height and weight, right? If somebody is extremely tall, let's say the average height in a population is 5'6". If somebody is 7 feet tall, it's also quite likely that they're quite a bit heavier than the average person, right? If somebody is quite short, it's quite a bit likely that they're also quite a bit lighter than the person of the average height. So these two variables, x and y, they tend to be far from their mean simultaneously in the same direction. So there's other cases where if x is big, y is very likely to be small, and vice versa. And so that's what covariance is measuring. So here's some examples. So we're looking top down onto density functions. So we'll start with this one here. This might be height and weight. So ignore the minus whatever. So just imagine this is like height and this is weight. So people who are taller tend to be heavier as well. That's why we see this kind of shape, because if somebody were out here, that would mean they're very short but extremely heavy, which is unlikely. There are definitely people who are all shapes and sizes, and that's fine. But on average, most of the people in our population are kind of clustering like this. Okay. So for this joint distribution, the covariance between x and y happens to be 1.5. All right. And you might imagine another situation like this where the covariance is 0. So these might be two measurements that don't actually really have a lot to do with each other. Like, I don't know, maybe height and high school GPA. There's not too much reason to assume that those should be related, or there should be any strong pattern in the data. So maybe our like scatter plot, top-down scatter plot of the population looks something like this, and this is a negative two variables, a joint density where the covariance is negative between them. So here, when x is far away from its mean over here, y tends to be far away from its mean in the opposite direction. So x is positively deviant from its mean. Y means y is likely to be negatively deviant from its mean, because you see some high density in this region, and similarly in this region. So that's a bit of a graphical intuition for covariance. Now, just because two variables have no covariance does not mean there's actually not a relationship between them. And so covariance, what I'm trying to say is that covariance is a kind of crude measure of a relationship. And it's because you're trying to boil down this entire joint density into a single number, right? So same with variance and expectation. Variance and expectation really are just summaries of marginal density. So you have this whole density function. It could be very complicated, bimodal, whatever. And you're just trying to boil it down into, okay, well, where can I balance it? And like how spread out is it roughly, right? So in general, this is a very crude measure, and same with covariance, except covariance, it's kind of even worse because now you have this two-dimensional density function that you're trying to boil down to a single number. So it's not really capturing everything, right? So here's an example where you have a joint distribution between x and y, and it's given by this. So here I just made x a normal distribution, and I made y conditional on x, also normal, but the mean of y changes with x squared. So when x is 0, the mean of y is about 0. But when x is like 2, the mean of y is 4. But also when x is minus 2, the mean of y is 4. So you get this kind of like curving relationship here. And for this joint distribution, the covariance is 0. And you can calculate that out. You can do your calculus and plug it into this if you want. But the idea is, again, that we're trying to measure like when x is far from its mean, is y typically far in a positive way or in a negative way? And in this case, when x is far from its mean positively, like the deviations cancel out. Like if you go left in x, y goes up. If you go right in x, y goes up. So those deviations cancel in this formula here, because a part here, the deviation from x that's positive, usually gives you the same number over here, the deviation in y, and when the deviation is negative, you have the same number over here, so those two cancel out exactly. And so you're taking like an average over a bunch of zeros. Okay, so that's a bit about the definition. Interesting little fact here. You may recognize that the self-covariance is just variance. So if I put here the covariance of x and x, what are you going to get? You're going to get the variance of x. So you can do that mechanically, right? Just plug in x where there was a y, and you get this formula here, which you should recognize as the variance of x. There's also this equivalent definition of covariance, which, again, starting from here, you can get by the same kind of algebra, just multiply stuff together, use linear of expectation, blah, blah, blah. And you will get to this definition, which looks a lot like the equivalent definition for variance, right? Which was the variance of x is equal to the expected value of x squared. But what's x squared? It's x times x, right? Minus the expected value of x squared, which is the expected value of x times the expected value of x. Okay, so you should see the similarity here. And of course, it has to be, because we know that if I put another x here, it has to be the same as this. So that all matches up. And you may recognize this is exactly the term that we were missing, in that when we decompose the variance of a sum of random variables, and we were saying, is that equal to the sum of the variances? And it was not. And the thing that we were missing was exactly this term times 2. All right, almost done here. So there's this other summary measure called correlation. What is correlation? It's just a scaled covariance. So the kind of more fundamental concept is covariance, and then correlation is a number that you can get from the covariance and the variances. So it combines the covariance and the marginal variances in a way that gives you a number that's always between -1 and 1. Because as we saw for in these examples, the covariance, it could be 0. It could be a positive number that's very large. So here it's 1.5. But if I had made this distribution really, really narrow and stretched out, that covariance could have been 20, 30, a million, and similarly negatives. And so to kind of compare apples to apples between distributions, sometimes you just want to look at you want to scale that covariance relative to the variances of the, or the spreads of the marginal distributions of x and y. And so this number, this correlation, is just defined as the ratio between the covariance and the product of the standard deviations of two random variables. And it turns out you can prove mathematically, this is in many of the reference textbooks, or you can ask ChatGPT to do this, it's just simple algebra, that this is going to be a number that's between -1 and 1. So the correlation between two variables is -1 if it's a negative relationship, where x goes up, y goes down, and 1 if it's the opposite. So how does this play with independence? We saw that for variance, the variance of a sum is equal to the sum of the variances if you have independence, and it's exactly because of this, right? So here, this covariance, this is the definition. We know that the expectation factors, if they're independent, and so this whole thing goes away. But no covariance does not mean that they're independent. Okay, so again, look at this example here. There's these random variables are clearly dependent. If I tell you what x is, you can tell me a lot about the likely value of y, right? If I tell you like x is 0, your guess y equals 10 is a very bad guess, right? But if I tell you, well, actually x equals 3, then your guess y equals 10 becomes a very good guess. So me telling you about x tells you about y, right? They're clearly not independent. However, the covariance is 0. So the covariance is not measuring independence. But it is the case that when they are independent, there is no covariance. So it's sensitive to independence, but it's not measuring it directly. This is the formula we already derived, variance of a sum. So here we can see about the case where this covariance can be negative. It's interesting. If x and y are not if x and y are increasing together, so when x is big, y is usually big. When you sum x and y, you're getting a kind of super additive effect. The distribution, you can play with this in R. You can do some simulations and convince yourself of this, like in draw random variables like this, and then look at the variance of the sum. You're gonna see it's more. But when you have two random variables that when x is small, y tends to be big, then this sum here, you're gonna get a lot of cancellations, right? So if you think about your population data frame, think about your top population data frame that has like x and y, right? If this is like -1 and this is 1, and then when this is -1, this is 1, and we have 2 here, this is -2, right? If you sum them up, you get x plus y, you're going to get 0, 0, 0, 0, right? A whole bunch of zeros. And the variance of all this is going to be very small. So when there's a negative correlation, these sums are canceling out, and the overall variability of the sum is going to be smaller than the sum of the variances. And in some cases, this can be actually, like in this example here, which is very extreme, I've made it so that this is exactly canceling this, and the overall variance is 0 of the sum. So you can get that case. So here's precisely such an example. We have x, y, and z is the sum of the two, and I'm just looking at the covariance of x and y, and the variance of z, and showing how these things are related. So this is exactly equal to here in this case that they are positively correlated. So this covariance is in this case 1, and we see that the variance is equal to the sum of the variances plus 2 times the sum of plus 2 times the covariance. This we already talked about.